P and Q, and here P and Q both prime and P is not equal to Q. This is one of the conditions. So that you should select P and Q. So, so that you should select P and Q in such a way that P and Q are not equal, but they are prime numbers. Then you calculate N. So N is the product of P and Q, then phi N. Phi N is equal to P minus 1 times Q minus 1. Then we select an integer E. Here E must be greater than 1 and E must be less than phi N. And here phi N and E should be relatively prime. Relatively prime means among these two numbers there should be no other factors. So the only common factors between phi N and E should be 1. So they are GCD. GCD is greatest common divisor, should be 1. So that means here phi N and E, they itself are not prime number. Like there is no such condition that phi N must be a prime number. Okay, definitely phi N is not a prime number because phi N is a product of P minus 1 and Q minus 1. And for E also, there is no such condition that E is always a prime number. But normally we select E from the list of prime numbers. Then it is much easier, because if E is a prime number, then definitely phi N and E, they are relatively prime, and the GCD of phi N and E is equal to 1. So the condition is E should be greater than 1 and E must be less than phi N. Okay, then we calculate D, and this calculation we did similar calculation in case of Hill cipher. So D and E, they are inverse, but they are inverse in mod phi N calculation. So here remember that they have not mentioned it here. E and D should be different at that point too. Okay, E and D should be different. If you find that E and D are same, so that means your encryption key and decryption key are same. Definitely, then this is not. We cannot use that algorithm, right? We cannot use those keys. So when you calculate E and D, you have to be careful. If you find that E and D are same, that means, say for example, you have selected 7 as E, and you find that the inverse of 7 in mod phi N is also 7. It might happen, okay? Then you should select another E instead of 7. Okay, so how? Go for maybe 9, 11, 13, the next number. Okay, so you should not select E so that E and D are same. So E and D must be different. If you find that your E and D are becoming same, then you should select another E. Okay, so how you can select? Just go for the next number. Then maybe you will find a different D. Okay, so but remember that E and D should be different. Okay, so write down that note also here. So then your public key will be E and N, and private key will be D and N. Okay, now in case of encryption, here another condition is your plain text M should be less than N. Okay, so what will happen if your plain text is greater than N? So then you have to like divide your plain text like block ciphers. Okay, so you have to divide your plain text so that the value of plain text is less than N. Okay, so in reality, how we use this? In reality, our n is a just a binary number, right? So say your n is 128 bit, or say 1000 bit, your n, then your plain text should be less than 1000 bit. Okay, so whatever uh, like the original format of your plain text is, it might be a video file or it might be a text file, whatever it is, just think that this is a long bit stream. Okay, because everything is byte and byte means bit. So you can take less than 1000 bit, then another less than 1000 bit. So then your m will be always less than n. Am I clear what I am saying? This part. বুঝা গেছে আমি কি বলছি?
জি স্যার।
মানে n এর যা লেংথ, n এর লেংথ যদি হয় 1000 বিট, তাহলে আমাদের m হবে অলওয়েজ লেস দেন 1000 বিট। তাহলে অবশ্যই অলওয়েজ m n এর থেকে ছোট হবে। So how we can find less than 1000 bit? Just consider that you have a very long bit stream. Then take first 999 bits, then next 999 bits. So your m should be always then less than n. So then what will be the cipher text? The cipher text will be m to the power e mod n. So if your n is less equal around 1000 bit, then definitely this is a very long calculation, m to the power e mod n, right? Very long, very lengthy calculation, and definitely this is not possible like with our calculator or these things. But remember that this is a very lengthy calculation, and that's why encryption or decryption in RSA takes longer period of time with compared to DES, because if you compare with DES, in DES there was no such calculation. Everything was like bitwise shift, XOR, rotate, and then take these bits, discard this number of bits. So those operations are way faster if you compare with this to the power e and mod n. Okay, so to the power e mod n is a very costly operation if you compare with XOR or NAND or AND, like so whatever we did in DES. Okay, so that's why public key cryptography is slower, much slower than uh, symmetric encryption. Okay, so for decryption, again we do the same thing. We take the ciphertext C, and then we uh, calculate C to the power D and then mod n. So it returns back m, and always remember that m is less than n. Now question is why it works, why RSA works. So RSA works because of Euler's theorem. We are not going to detail. So Euler theorem says that a is just here, like GCD a and n is equal to 1. So then if you take a, and a to the power phi n mod n is equal to 1, remember that your GCD of a and n is equal to 1. So if this condition is true, what we have on the right hand side, that is GCD a n is equal to 1, then Euler's theorem says a to the power phi n mod n is equal to 1. And what is phi n? Phi n is here, phi n is p minus 1 times q minus 1. Okay, so we're not going to the proof of the Euler theorems, but if you just consider that this is true, like a to the power phi n mod n is equal to 1, then you can understand why RSA works. Okay, so just consider that Euler's theorem is true. So then in RSA we have n is equal to p times q, so phi n is equal to p minus 1 times q minus 1. Then we have to choose E and D, and we have said that E and D are inverse in mod phi n calculation. So if you multiply E and D then E and D will be 1 in mod phi n calculation, right? Otherwise, they cannot be inverse of one another. So when they are inverse of one another, normally in our regular calculation, inverse means if you multiply two numbers, then the product is 1, right? So say 2 by 3 and 3 by 2, they are inverse of one another, right? Why? Because if you multiply these two numbers, then you get 1. So that's why they are inverse of one another. So similarly, E and D, they are inverse of one another. So if you multiply E and D, you get 1, but 1, not regular 1, 1 is in mod phi n calculation. Okay, so E and D, if you multiply, then E and D will be equal to 1 plus k times phi n. Okay, so if you recall in our mod 26, right? In our mod 26, okay, let me remember, 3 and 9, they are inverse of one another, right? In mod 26 মনে আছে না mod 26 এ 3 আর 9 কি ছিল একটা আরেকটার ইনভার্স ছিল কেন because 3 times 9 is equal to 1 plus k times 26 k times 26 what is the value of k here এখানে k এর ভ্যালুটা কত ছিল কেউ কিছু বলেন না কেন 3 times 9 is equal to 1 plus k times 26 then what is the value of k here
1
1 বোঝা যাচ্ছে k is equal to 1 so then we said that 3 and 9 they are inverse of one another in mod 26 calculation so just replace that mod 26 with phi n okay so E and D will be inverse of one another that means E times D is equal to 1 plus k times phi n for some k what is the condition of k k should be always integer or real k কি হতে হবে অবশ্যই এখানে integer না real
integer.
integer k is always integer here so for any integer k if you can prove that e times d is equal to 1 plus k times phi n then we say that e and d are inverse but they are not regular inverse they are inverse in mod phi n calculation okay so when you select e then you calculate d and if you say that okay I have found this e and d then definitely this line is true that is e times d is equal to 1 plus k phi n যদি আমরা কোনো একটা ক্যালকুলেশন দেখতে চাই সে ফর এক্সাম্পল হিয়ার n was p times q that is 187 so phi n was 160 then we say that e is equal to 7 আমরা এটা সিলেক্ট করছিলাম e is equal to 7 so d times e look the same equation d times e is equal to 1 mod 160 why 160 because here phi n is equal to 160 so e যদি 7 হয় then we conclude that d is equal to 23 why because 23 times 7 23 times 7 was 161 which is equal to এখানে একটা ভুল ছিল রাইট which is equal to এই জিরোটা হবে না আর কি এই জিরোটা হবে না which is equal to 1 times 160 plus 1 just discard this zero because this is 161, which is equal to 1 times 160 plus 1. So again here k is equal to 1. So that's why 23 and 7, they are inverse. They are inverse, but they are not regular inverse. They are inverse in mod 160. So that's why we can take E and T. Okay. So same thing here. If you take E and D as inverse of one another, then E times D should be 1 plus K times phi n for some K, for any K. এরকম হতে হবে। এটা হলেই শুধুমাত্র E আর D কে নেওয়া যাবে। Otherwise, you cannot take E and T. Okay, now, why it works? Why RSA works? Again, remember that this is true. Okay, এটা কিন্তু আমরা ধরে নিচ্ছি যেটা ট্রু। এটা অয়লার্স বলছে ট্রু, প্রোভাইডেড দ্যাট দিস ইজ স্যাটিসফাইড। এটা স্যাটিসফাইড না হলে আবার এটা হবে না। So now c to the power d, এটা কি করি আমরা ডিক্রিপশনের জন্য, রাইট? ডিক্রিপশন মিন্স c to the power d. So c to the power d means m to the power e. m to the power e টা কি ছিল? c. m to the power e ছিল c. So we are just replacing c with m to the power e. So c to the power d means m to the power e times d. আর e times d মানে কি? e times d is equal to 1 plus k phi n. So this is equal to m to the power 1 plus k times phi n. So which is equal to m to the power 1. আমরা আলাদা আলাদা করে just we are dividing 1 and k times phi n. So m to the power 1 times m to the power phi n times k. Okay. Now what is m to the power phi n? Euler says that এটা কিন্তু a means যে কোনো a. Okay. So a to the power phi n mod n is equal to 1. So Euler says that m to the power phi n is equal to 1. So that's why if we replace that, then it becomes m. That's why it returns back the plain text m. Okay. So that's the reason RSA works. Now, if we look at the security part of RSA, here is another example. I think we have another example at the end. Yeah, here we have another example. So I recommend that you must go through these examples and do the math by yourself. Okay, যে করে দেখা যে আসলে ভ্যালুগুলা কি আসতেছে। So this is not a very big example. The numbers are not so big. So 7 and 13, they are manageable. And n is 91 and phi is equal to 72. Okay, now tell me from here. So which part is known by the attacker? From this list, what are the numbers we have? We have p, we have q, then we have n, then we have phi n, and now e and d. So which part is known by the attacker? The attacker always knows the public key. So e and n are always known by the attacker. এটা যে কেউ জানে, right? Because this part is public. The attacker does not know. The attacker does not know p, then q, then e. Sorry, d. So these values should always remain secret. So if somehow from e and n the attacker can trace back to p, q, and d, then the security of RSA is compromised. Now the question is, what is needed to calculate p, q, and d from e and n? Okay, so if I know e and n, then definitely what do I know about n?
P into Q.
Or In general, n is a factor of what? N is a factor of, what do I know about n as an attacker?
Two prime numbers.
Exactly. I know that n is a factor of two prime numbers and only two prime numbers. There are just two factors of n and they are two prime numbers. So there are no other factors. One is always there. So one নিয়ে তো আমার মাথা কামানোর কিছু নাই. But other than one and the number itself, there are only two factors and those two are two prime numbers. So if I can find those two prime numbers, that means then I can find P and Q. So if I can find P and Q, then definitely I can calculate phi n. And if I can calculate phi n, then I know that D and E are inverse of one another in mod phi n calculation. So definitely I can trace back, and remember that D and E are unique. Unique means for a specific E, there exists only one such D. Okay, it's not like that there are many D's like that. There are only one such D, so that D and E are inverse in mod phi n calculation. So if I can calculate P and Q, I can calculate phi n, then from inverse calculation I can calculate D. So I can calculate the private key. So the only security factor is here whether I can find P and Q from n. So if I can break this factorization, then everything is compromised. Okay, so it looks a very simple problem, but RSA says this factorization, like finding these two factors, must be hard. আমরা বলে আসছিলাম না যে hard and easy, right? So more generally the hard problem is known. এখন নিশ্চয়ই বুঝা গেছে কি বলতে যাচ্ছে. I know the problem. The problem is find out P and Q from n. So the problem is known. What I have to do, I know, but this is made hard enough to be impractical to break. Okay, so what is the only way to make it impractical to break? We have to select very large numbers. Okay, so if you select small numbers, then everything is compromised. So that's the only security factor here. বুঝা গেছে? Any question about this? Okay, so four possible approaches to attacking the RSA algorithm. The first approach is brute force attack. Remember that brute force attack is always there, always there. So these involves trying all possible private keys. So I know the value of E and N. I don't know the value of D, but D must be less than N, right? D must be less than N. Why? Because D is less than phi N and phi N is less than N. So definitely D must be less than N. So what I can do, I can keep trying every single numbers. কোনো না কোনোটা তো হবেই, আমি একটা একটা করে ট্রাই করা শুরু যদি করি, so definitely D must be one of the numbers in between 2 to n minus 1. So what I can do, I can keep trying from 2 to n minus 1, and if I get the luck, I will be able to break the keys. So that is brute force attack. This is always there. Again, how we can prevent brute force attack?
Key length is very large.
Key length is very large, exactly. Simple solution. Now, the second problem is mathematical attack. This is the one just I have explained. There are several approaches all equivalent in effort to factoring the product of two primes. So there are several algorithms in mathematics how to find out the factors. Like those who were or are involved in programming contest, you definitely know there are different algorithms. Like these types of math, there are different types of algorithm, right? আমরা যেটা নর্মালি মনে করি যেভাবে করে আগাতে হবে তা না, there are some shorter ways, shorter path. So you don't have to search all the values to find out the factors. Okay, definitely the easiest way is just take half of the number and then keep searching from 2 to half of the numbers. Okay, then definitely you will find the factor. But again, that is not the way. In mathematics there are other ways. Now the third attack, I have not studied in detail, so I cannot tell you the whole thing, but it says that these depend on the running time of the decryption algorithm. So from the running time, you can gauge the length of the keys. Okay, because there are some other mathematical relationship, like how long it takes in these types of machines, in these number of cores. So from those mathematical equation, you can gauge the length of the keys, and then you can um, like limit your search space. You can reduce your search space. So another attack is chosen cipher attack. This type of attack exploits properties of the RSA algorithm. Again, this is like 3 and 4. These two are research areas. Okay, like how you can break RSA. The thing is, whenever you propose one of the cryptographic algorithms or any security protocols, then other researchers, they try their best to break that protocol or to break that cryptographic system. Okay, because if they can break that, they can definitely publish a very good paper, and this is a research work and it has some scholarly values. Okay, so that's why they try their best to find out flaws. So that's why in research there are other type of attack who exploit the properties of the RSA algorithm, and those attacks are in the categories of chosen ciphertext attacks. But remember that whatever attack we say, the only the only protection we have is you have to extend the length of the keys. So that is the only important issue here. Like the length of the keys must be very large. Here the length of the keys means the length of P and Q. Okay, because P and Q defines everything. Now, how to resist brute force attack? This is same for RSA as for other crypto systems. Use a large key space. The larger the number of bits in D, the better, because the calculations involved both in key generation and in encryption and decryption. Okay, so the larger the size of the key, the slower the system will run. That is the problem. Like I can take arbitrarily a very, very large key, but then my system will be slower. So again, that factoring problem, mathematical approach takes three forms, like factor n, then phi n, then determine phi n, what I have just explained. So for a large n with large prime factors, factoring is a hard problem. Okay, but it is not as hard as it used to be. So before, we did not have like multi-core processors, and we could not run so many threads in parallel and all those things. And we did not have GPU and other processing units. But now, with those hardwares, this is not so hard as it was before. আগে যত ছিল এখন আর সেটা নাই, সেটার কথা বলছে. So here they have given some example, but if you look at the dates, like all are dated back. Okay, say for example 2005. So এটা আসলে অনেক আগের কথা বলা হয়েছে. So right now these numbers are obsolete, but from these numbers you can have some idea. Okay, like why we are extending the number of bits. So here they have given some numbers based on MIPS. MIPS is an unit. It means a million instructions per second. So say you have a processor, that processor can run how millions like instructions per second. So that is the unit of your timing. So if you can run 1 million instruction per second, then if you consider that processor, then if you consider that that processor is running for 1 year, so every second you are running 1 million instructions and that processor is working for 1 year, then that is known as MIPS year. Okay, so MIPS means million instruction per second. Then if it runs for 1 year, then it becomes MIPS year. So they have given the numbers in MIPS year. Okay, say for example, if you consider this example, so if you have 155 decimal digits in your number, so you have a very long number, and in that number, how many digits you have? You have 155 digits. Then the key length will be 512 bits. Okay, so there is a mathematical relationship. If you have 512 bits, then in general it becomes 155 digits approximately. So in August 1999, the processors you had at that time, remember that the processors you had at that time, so if you want to break the RSA keys, which RSA keys? The RSA keys that have 512 bits in length. Then that processor at that time, it took 800 years to break the RSA key. Sorry, 8,000 years. So 8,000 years is a very long period of time, and you can consider that that was like we used a term, right? Yeah, you can consider that that was impractical to break. Okay, so that was not unbreakable, but that was impractical to break. So এটা হচ্ছে 1999 এর হিসাব. Okay, so now definitely if you use that PC or that processor now, you cannot break 2 days RSA. Why? Because in these days our key length is not 512. The key length has been increased. So if you want to use that processor now, you cannot. But on the other hand, if you can use 2 days processor, like the processor we have, say even in our cell phone or in our laptop, and if you want to break a 512 bits key, maybe you can break it in few seconds, okay, or maybe in few hours. So that's why we have to definitely increase the number of bits. So the key point is your number of bits will always depend on the processors you have at that time. Okay, so যদি আমি if I consider after 10 years, then maybe I have to increase the number of bits, because we can predict that in 10 years we have much better processors. Okay, তো সেই কারণে আমাদেরকে সবসময় এই কি লেন্থটাকে বাড়ায় যেতে হচ্ছে, এটাই হচ্ছে কথা আর কি। তো আমি এটাকে বাড়ায় এমন একটা জায়গাতে রাখবো যাতে ওই সময়কার প্রসেসরের জন্য এটা ইমপ্র্যাকটিক্যাল হয় ব্রেক করা। এটা হচ্ছে মেইন ফ্যাক্টর পয়েন্ট আর কি এখানে। Okay, so here they have explained for this example for 7 and 13 what will be the possible values. So for 7 and 13, n will be equal to 72. So for 72, what will be the chosen E, what will be the value of E. So you cannot take 2 because 2 is GCD of 2 and 72 is not equal to 1, so it does not work. So even 3 does not work because 3 and 72 they have a factor, and that factor is 3 itself. So since 2 does not work, definitely 4 does not work also. So they have tried E is equal to 5, and E works because GCD of 5 and 72 is equal to 1. Now, if you select E is equal to 5, what will be the value of D? Remember that E and D should be inverse in mod phi n, and here phi n is equal to 72. So E and D should be inverse in mod 72. So if you multiply E and D, you should have 1 plus k times 72. Okay, that's what they have explained here. So finally they have found that if you take D is equal to 29, then 29 times 5 is equal to 1 in mod 72 calculation. So this is your private key. So here they have shown how you can encrypt m is equal to 10. So you have to calculate 10 to the power 5 mod n, which is equal to 82. Then you have to calculate 82 to the power 29. Okay, so in the exam, remember that you have to show me the calculations, like whatever the way you are using. So if you just write down this single line, okay, then I am not going to give you marks, because I know that this is not possible to calculate 82 to the power 29 using your calculator. Okay, so definitely you have to break down. So I want to see how you calculated the smaller steps. Okay, so আমি এই ডিটেলটা আমি দেখতে চাই যে কিভাবে করে করছেন. So what they are doing, they are calculating to the power 1, to the power 2, to the power 4. I'm not sure if this is helpful. Maybe this is good for programming, but I'm not sure whether this is helpful. Rather, if I have to calculate this, I will take, say for example, 29, then maybe I can calculate to the power 5 5 times, and to the power 4 1 time. মানে 29 কে আমি হয়তো ভেঙে ভেঙে 82 to the power 5 এটা ক্যালকুলেট করে তারপরে হয়তো আমি করব. সো ইটস আপ টু ইউ হাউ ইউ ওয়ান্ট টু ক্যালকুলেট. তো আমাকে করতে দিলে আমি 82 to the power 5 এটা হচ্ছে 5 টাইমস করব, and 82 to the power 4 I will calculate that one time. So then in total it will be 82 to the power 29. Then I will have some smaller numbers, and from those smaller numbers I can calculate eventually 82 to the power 29. So here they have calculated the smaller numbers too, but they have calculated to the power 16, to the power 8, to the power 4. I'm not sure whether this is helpful. আমার মনে হয় না, কারণ এগুলা করতে গেলে আমাকে তো সবগুলো আলাদা আলাদা করে আসতে হবে. Whatever, they have done that, and then finally you have to calculate the multiplication of these four numbers. এটা ওরা দেখায় নাই, কিন্তু you have to do that. Then that multiplication will be a small number, so you can calculate using your calculator that multiplication and mod 91. So if you do that, you should have 10 mod 91. So we concluded that 82 to the power 29 mod 91 is equal to 10, and 10 was our plain text, that is M. So they have shown that after encryption you get 82, and after decryption it returns back 10. So you have the same number after decryption. So I think that's all from RSA. So we are going to take a class test or quiz, whatever you say, in your next class, and the topic will be RSA. So whatever we have discussed from the starting point of this slide, এখানে যা আছে স্লাইডের প্রথম থেকে শেষ পর্যন্ত। Okay, any question? Okay, no question. So those who submitted in email, be careful. You must submit using our LMS. Okay, so if you have to, I don't know how you can practice. I have no idea. And this is so simple. So I really have no idea what you need to know or what you need to do to submit a PDF file. This is just simple as sending an email. আমার আসলে ধারণা নাই যে এটা কেন মানুষ পারে না বা কেন মানুষ পারবে না, আমি জানি না। Okay, I really don't have any suggestion, but remember that you must submit using LMS. And another point is, if you copy, I have found in the midterm that some of you have copied. Okay, so I did not do anything for that copying part, but from now on, if I find any copy, I am going to give you 0. Definitely remember that. Okay, any of you, আমি কিন্তু কপি পেলে আমি কিন্তু এবার 0 বসাই দিব একদম, ডেফিনেটলি আমি বলে দিচ্ছি। মিডটার্মে কিন্তু আমি দেখছি, আমি কিছু করি নাই। Okay, so now we want to move to our next topic. Slide দেখা যাচ্ছে, right?
Yes, sir.
Okay, so we are going to study Diffie-Hellman, that is another public key cryptography. But before that, I want to change the topic. So that's why we want to study cryptographic hash function. We will return back to Diffie-Hellman after we conclude this topic. So this is another very important topic, very important part of cryptography, that how you can calculate cryptographic hash function. Okay, just give me 1 second. Okay, So this is another very important topic, and whenever you think about even public key cryptography, you cannot use public key cryptography alone. You will always find that somehow the hash function is always mixed with that, especially if you consider about digital signature. You need two things: you need hash function and you also need public key cryptography. So normally we don't use public key cryptography alone, we use hash function too. Just wait. Hello. Okay, I'm sorry for that. Okay, so now what are the key points here? We want to study hash functions definitely, but this is not a regular hash function, because if you look at the title, it says that this is cryptographic hash function. So with regular hash function, we are going to add something else so that it becomes cryptographic hash function. So first we want to study what is a hash function, then we want to see how we can develop a cryptographic hash function from a regular hash function. So a hash function maps a variable length message. Can you hear me?
Yes, sir.
Okay.
Yes, sir.
Okay. So a hash function maps a variable length message. Look at the part, it's a variable length. So the message might be very small or the message might be very large. So the good thing here is there is no limit or no characteristics of the length of the message. It might be very long message, or it might be a very small message, even say few bytes, no problem with that. So whatever the length of the message is, a hash function maps, okay, maps a variable length message into a fixed length hash value. So the output of the hash function is fixed length. What is fixed length? Say 32 bits, or say 128 bits, or maybe 56 bits, or 64 bits, whatever the length is. This is always fixed, and this is very small, this fixed length output. So this is known also as message digest. Same thing, hash or the message digest. So all cryptographic hash functions involve the iterative use. So iterative means you use the same hash function several times. Okay, maybe 2 times, 4 times, 5 times. So iterative use of a compression function. So hash function, they use the compression function several times. So the compression function used in secure hash algorithm falls into one of the two categories. So a function specifically designed for the hash function, and then an algorithm based on a symmetric block cipher. Okay. So here SHA, or in short we say SHA, and whirlpool are examples of these two approaches. So we will see how we can calculate the SHA. We are not going to study whirlpool, but we are going to study SHA. Now, if you think that hash function is H, then H accepts a variable length block of data as input, and it produces a fixed size hash value. So M is the message, that is the variable length message, and small h is the digest, that is the fixed length hash. Okay, so say M is arbitrarily large, or M might be very small, but small h is always fixed length, and it depends on which hash function are you using. There are several of hash functions, so they may have different length, but for a specific hash function, the h is always fixed, the small h. Now, what is a good hash function? The good hash function means when you apply the function to a large set of inputs, will produce outputs that are evenly distributed and apparently random. Okay, so here remember that this is one kind of mapping. So if you can remember what I'm saying about mapping, so now we have two different domains, right? So say this is the domain of M. M means the messages, and say this is the domain of H, small h. So when you consider a point from here, that will map to a point here. So if you consider another point, that will map to another point. So this is the mapping part. Okay, so I will give you the value of capital M. Through this mapping or through this calculation, you will find out the value of a small h. So a good hash function, applying the function to a large set of inputs. So say M are distributed here. Okay, so from this large domain, M are evenly distributed and many places. So this should produce outputs that are evenly distributed. Okay. Now, what is h? Say h is equal to, say very small, I can consider, say h is giving value, say from 0 to 63. So 0, 1, 2, up to 63. Finally, you have 63. Okay, so 63 means this is how many bits? 8, no, not 8 bits, 6 bits, I think. Okay, whatever. Now, if you find that whatever value of M is, say you always find the value of H, which is from 0 to say 31. So whenever you calculate hash, you find say 0, 5, 7, 9, 31, 28, 29, 27. and hardly, very few times you find say 50, 54, very few times. So then can we say that the value of h is evenly distributed? Can we say that?
No, sir.
No. Why? Because the values are always biased, and the values, most of the times we find that the value is upper half of the value of h, from 0 to 31, and hardly we find from 32 to 63. We find, sometimes we find, but maybe say 90% of times we find that values are mapping, that is whatever value of m we give, it calculates small h and returns back the value, and we find that most of the times the values are distributed from 0 to 31. Then definitely we should say that this is not evenly distributed and they are not apparently random. So this is not a good hash function. Okay, so a good hash function, when I give you a large set of input of m and you calculate and you find h, and the value of h are always distributed. Remember that it does not mean that for two different m you cannot find the same value of h. Definitely you can find, because you have only 64 different values of h. Only 64 different values of h. So if I calculate this h function 100 times, so definitely I will have repetition, different types, different times, more than one times I will find repetitions. So it may happen that for two different m you are finding the same value of small h. যেহেতু স্মল h এর ভ্যালুটা 0 থেকে 63 এর মধ্যে, সেই কারণে আমি যদি 100 বার ক্যালকুলেট করি এই হ্যাশ ফাংশন, তাহলে অবশ্যই কোনো না কোনো বার আমি দুইটা সেম ভ্যালু স্মল h এর পাবোই। If you calculate 100 times the value of hash function, then definitely, because you have only 64 different values and you want to calculate 100 times, so theoretically at least 34 times you will have repetitions. So this is very common that for two different m you may find the same value of small h. Now here comes the other properties. Okay, those properties are very interesting. Remember what I have just said. Okay, now the principal object of a hash function is data integrity. What does it mean? It means if you change the value of m even the slightest part. What is the slightest part? A single bit. Okay, say consider that you have 500 megabyte file. So in a 500 megabyte file, one bit is nothing. But if you change even any bit, they have said that a change of any bit, there must be high probability that in a change to the hash code. So consider that you have two different m. One is m1 and another is m2. They are almost identical. You have only one bit change between m1 and m2. But a good hash function will end up with two different h. Then we will say that this is a good hash function. Then what will be the use? The use is data integrity. Okay, so data integrity means, say you have a very large database and at the end of the day you calculate the hash of the database and you store that hash of the database in some secured place, and the database is open, anybody can access the database. Now if someone with bad intention, or maybe due to some hardware failure or some read write failure, whatever the reason is, one bit in your database has been changed. So when you come to your office next day, the first thing you do, you calculate the hash of the database, and you compare that hash with the hash you stored in a secured place. So if you find that these two hashes are same, then you conclude, okay, nothing has been changed in my database. But if something has been changed, then definitely a good hash function will produce two different age. The stored one and the newly calculated one will be different. So then you can easily identify something has been changed. So the same thing we use in case of data transmission. So when we transmit data through internet or through any other medium, then we send the data, we also send the hash of the function. So at the receiving part, the receiver also calculates the hash and compare with that hash with the received one. So if they are same, then the receiver concludes that the data integrity has been satisfied. So if something is wrong, and remember that if you send that, so that means I'm saying that from A to B, I'm sending a message M, and I'm sending the hash of the message too. So I'm sending M. This is a comma. Okay, just consider my bad writing here. And I am also sending the hash of the M. Okay, just make it uppercase here. Now, at the receiving end, the B will recalculate the hash and will compare with the received hash. So this way we can provide data integrity, but remember that this is good for error detection. This is good for error detection. Okay, definitely this is not possible error correction from here. That is another story. I'm not going to that detail, but this is not good for data integrity in case where attackers are also there. Why? Can somebody tell me?
If a attacker receive the message and can read the message, he can also generate the hash file again, and he will alter the message, and along with the message he also altered the hash.
Exactly, very good answer. So if somebody intentionally change the message to M prime, he can also calculate the hash of the M prime. So he can change both the message and the hash together. Then the receiver cannot detect that this has been changed. Okay, so this method, that is I'm sending the message and its hash, is good for only for error detection. So the error detection and the attack scenario, they are two different cases. Remember that error detections is coming from general networking, where we want to protect the data from any kind of unintentional error. Error means something unintentional, something has been happened that we were not ready or we did not want, but maybe error is coming from hardware or maybe software. It may happen in data transmission, or maybe my network card was faulty, or maybe the network card of one of the routers were faulty, or when the data is going to queue and when the data was coming out of queue, error may happen. Okay, error may happen for hundreds of reasons. Say for example, when we transfer data from our USB to our hard drive, we are not transmitting, actually just copying from USB to hard drive. Even in that case, we have found that error may happen. Okay, so that is the like slightest transmission, like just from my USB, I am copying it to my hard drive. Even in that case, error may happen. So in data transmission, error is very common, and especially in these days, we use Wi-Fi or Bluetooth. That means wireless transmission, and in wireless transmission especially, error is more common. Okay, very common with compared to wired transmission. So for those error detection part, hash is quite okay, fine. But if you suspect that there might be some attacker and who can intentionally change the value of my message, then only hash is not enough. So in that case, you need some cryptographic hash. Okay, so that's why we need cryptographic hash. That's my key point here. Okay, now what is cryptographic hash function? So cryptographic hash function needed for security applications. Okay, just what I have explained. We need it for security purpose. So an algorithm for which it is computationally infeasible to find either. Okay, so again, these are the properties of a good cryptographic hash function. So what are the good properties? What are the properties of a cryptographic hash function? So a cryptographic hash function, they have said that computationally infeasible. Why? Because no attack is significantly more efficient than brute force attack. So brute force attack is always there. Okay, so that's why they have said that brute force attack will not be computationally feasible here. So what are the properties? A data object that maps to a pre-specified hash result, this is known as one-way property. So what is one-way property? One-way property is you will find a data object that maps to a pre-specified hash result. Okay, so that means, just 1 second, I have a call from university. Hello, assalamualaikum, madam. হ্যাঁ 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 মনে আছে, হ্যাঁ প্রথম 2 সেমিস্টারে। হ্যাঁ হ্যাঁ আচ্ছা ঠিক আছে। Okay, so we want to find a data object that maps to a pre-specified hash result. That means I will give you, remember that what I said here on the top. I said that this is possible, that if you calculate the hash for several times, say I have 64 different values of age and I'm calculating hash for 100 times, then definitely at least 34 times you will find that two different m are mapping to same age. ওকে, একটু কি বুঝা গেছে, রাইট? এই কথাটা কি বলছিলাম?
Yes, sir.
Okay, now I'm saying what I'm saying, it may appears contradictory at first, but if you understand carefully, then you will find this is logical. I'm saying that if I give you a specific age, now you cannot find out the m that maps to that age. Okay, so I'm giving you the other way around. That means I'm giving you the value of age, and now I'm saying that can you find an m that maps to age? No, you cannot find that. This is not computationally feasible. So if that is true, then this is a good cryptographic hash function, and this property is known as the one-way property. So the one-way property says that a data object that maps to a pre-specified hash result cannot be found in computationally feasible way. It might be found because they have said that brute force attack is always there, but maybe it will take 100 years or maybe 200 years or something like that. বুঝা গেছে কি বলছি?
Yes, sir.
So I
স্যার
will,
আমরা হ্যাশ থেকে কখনোই মেসেজটা আবার ফেরত পাবো না, তাই তো?
না এটাও ঠিক বলি নাই। এখানে বলছি যে আমি শুধু হ্যাশটা দিয়ে দিব। এখন মেসেজের তো কোনো ডোমেইন নাই। এখন অ্যাটাকার কখনোই এরকম কোনো মেসেজ খুঁজে বের করতে পারবে না যেই মেসেজটা ক্যালকুলেট করলে ওই এইচটা পাওয়া যায়। এখানে কেন স্পেসিফিক মেসেজের কথা বলা হয় নাই যে হ্যাশ থেকে ওই একটা মানে ব্যাপারটা এরকম না যে আমি এম নিছিলাম, সে আমি M1 নিছি, নিয়ে M1 থেকে আমি ক্যালকুলেট করে H1 পাইছি। এখন অ্যাটাকারকে বলা হচ্ছে যে তুমি M1 খুঁজে বের করো, আমি তোমাকে H1 দিছি। নো, ইটস নট লাইক দ্যাট। আমি অ্যাটাকারকে শুধু H1 দিয়ে দিছি, দিয়ে বলছি তুমি যে কোনো এম খুঁজে বের করে আমি আসো, সেটা M1 হোক আর হোয়াট এভার এম হোক। তুমি এমন কোনো এমই খুঁজে বের করতে পারবা না যেই এমটা এই এইচ এর সাথে ম্যাপ করে, H1 এর সাথে ম্যাপ করে। So then this is known as one-way property. বুঝা গেছে?
Yes, sir.
Because they have said that you cannot find a data object. A data object কিন্তু বলছে, এটা কিন্তু বলে নাই যে previously calculated data object, just বলছে a data object, that means any data object that maps to a pre-specified hash result. আমি একটা স্পেসিফিক হ্যাশ রেজাল্ট বলে দিছি, সেটা থেকে তুমি এমন কোনো এম খুঁজে বের করতে পারবা না। ওকে, নাও the second part, that is the collision free property, is related to one-way property. They have said that two data objects that map to the same hash result cannot be found. Okay, two data object মানে আমি কখনোই এরকম পাবো না যে আমি M1 ও খুঁজে বের করছি and আমি M2 ও খুঁজে বের করছি। খুঁজে বের করে I will never find that both of them are mapping to the same age. Okay, so what will happen then? If I can find two different M that map to the same age, then I can change them easily. I can use them interchangeably. আমি যে কোনো সময় চাইলেই M1 কে M2 দিয়ে রিপ্লেস করে ফেলতে পারবো বা M2 কে M1 দিয়ে রিপ্লেস করে ফেলতে পারবো। So this is known as collision free property. Okay, but remember that previously we have said that collision is very common, but collision is random. That's why I cannot find intentionally two different M that map to the same age, but I definitely know that it is possible. ওকে, কিন্তু আমি ইন্টেনশনালি, মানে এটা র্যান্ডমলি আমি পেয়ে যেতে পারি হয়তো খুঁজতে খুঁজতে খুঁজতে, সেটা অন্য কথা, কিন্তু ইন্টেনশনালি আমি এটা খুঁজার উদ্দেশ্যে বসলাম যে আমি এরকম দুইটা এম খুঁজে বের করতে চাই যে দুইটা এম সেম এইচ কে ম্যাপ করে, সেটা আমি খুঁজে বের করতে পারবো না। সো দেন দ্যাটস ওয়াই দিস ইজ নোন অ্যাজ কোলিশন ফ্রি প্রপার্টি। Now, this is often used to determine whether or not data has changed. Now, we definitely know why. So if we look at the diagram, we have a message or data of block M, and this is a variable length. And then we add the L bits. L is the length of this message. And then we pass this through the H function or the hash function, and it calculates the hash value small h, and this is fixed length. So in the diagram, you can easily find why this is a trapezium and why this side of the trapezium is much bigger than this side. Why? Because this might be a very large message, but the length of small h is always fixed, and this is small. সেই কারণে এটাকে ছোট করা হয়েছে এবং এটাকে বড় হিসাবে দেখানো হয়েছে। So what are the use of cryptographic hash function? So cryptographic hash function is used in message authentication. So achieved using a message authentication code or MAC. এটা আমরা ইউজ করছিলাম, রাইট? আমরা আগে এটা ইউজ করছি MAC শব্দটা। MAC is message authentication code. This is also known as a keyed hash function. So this is a hash function. With the hash function, we mix one of the keys. আমরা শুধু হ্যাশ ফাংশন ক্যালকুলেট করি না, হ্যাশ ফাংশন ক্যালকুলেট করার সময় আমরা কিটাকেও অ্যাড করে দিই। So the another use is in digital signature. So similar to that of the MAC, the hash value of a message is encrypted with a user's private key. It is a digital signature. So definitely we are going to study it, study the digital signature. And this is also used in one-way password file. Okay, definitely we know that in a good system, the actual password is not saved. Okay, and we always say that this is a very bad practice if you store the actual password. Why? Because someone from insider, ভিতরের কেউই, they can steal the password. Okay, so if they can steal the password, say if your password of your Facebook account was stored, like if they stored the actual password, then someone from Facebook, they can steal say 1 million password, and definitely you can guess what will be the price, what will be the cost, like what is the money he can earn just by selling those passwords in black market. Okay, so for in digital world there is also, remember that there is a parallel black market where data is being sold, যেখানে ডেটা কেনা বেচা হয়। ওকে, সো সেখানে এরকম পাসওয়ার্ড কেনা বেচা, ইমেইল অ্যাড্রেস কেনা বেচা, আমাদের পার্সোনাল ইনফরমেশন কেনা বেচা এগুলা হয়। দেয়ার ইজ এ ভেরি বিগ মার্কেট। সো a good system, they never store the actual password. Instead of that, they store the hash of the password. Okay, so always your hash of the password is being stored. So what happens when I enter my password in one of the sites? So when I enter my password, then my browser knows which hash function the browser will use. So the browser also calculates in my browser end. Remember that this is being calculated even before transmission. So even your password is not being transmitted. So the browser calculates the hash of the password, and your hash of the password is being transmitted. So that hash of the password is compared with the hash of the password they have stored in their database. So from that comparison, they can say whether you have entered the correct password or not. So what happens if my hash of the password is stolen? If somebody stole it from that database, then they can do nothing, because from the hash of the password, they can never return back to the actual password. Why? Because we have already explained that here. Okay, so now if you put the hash of the password, the browser will again calculate hash of that. So the browser will send actually the hash of the password. So that means it will produce totally different value. So in fact, there is no use of your hash of the password. Okay, so that's why this is used. That's why we use hash function in storing password. Okay, hash is also being used in intrusion detection or virus detection. So the antivirus we use, the popular antiviruses, all the antiviruses we use, they do nothing. They just produce hash of a good healthy file, and they know the hash of an infected file. Okay, because remember that we have to download the virus definition time to time. Okay, so if you store, like if you install say 2000 Norton 2000 in your machine, you will find that it will take few hours to update the definition file. So what is that definition? That definition file is the hash of infected files. Okay, why? Because a specific virus attacks to specific files. একটু মাইক্রোফোনটা বন্ধ করলে ভালো হতো, কারো একজনের মাইক্রোফোন অন করা। So a specific virus attacks to specific files. Most of the times they attack exe or DLL or those types of files. So the virus definition knows, or in the virus definition file you have hash of those infected files. So whenever I download my virus definition, that means I download the hash of those infected files. So then in my machine or in my desktop, when I say scan for probable virus attack, it compares my hash of my exe file with the definition file. Okay, then it can identify whether there is an attack or not. So that's why if you run your virus scan in an empty machine, maybe it will take say 15 minutes. But if you run in your machine, maybe it will take few hours. Why? Because this is a very dumb program. The antivirus we use, this is the dumbest program I can ever imagine. So if in its definition file, it does not have the definition of a newly like propagated virus, it cannot detect that virus at all. Okay, so this is not smart at all. This is a very dumb program. It compares all the existing files you have with the all definition files you download. Okay, so that's why this is not smart, and that's why it can never detect a very new virus. Okay, unless you have downloaded the definition of that virus. So the intrusion detection, we also do the same thing, like the similar thing. So in intrusion detection and virus detection, we can also use the hash function. Now, for message authentication, we have 4 different ways. I think we have explained maybe some of the ways. Okay, let's start from the first one. So say I have a message M, and like from source A, we want to send it to destination B. So I am calculating the hash of this message, and then I encrypt that hash of this message with one of the symmetric key K. Okay, no, sorry. I encrypt the whole message, also the hash of the message. Okay, so I am encrypting the whole message and I am encrypting the hash of the message. So what I am doing, I am encrypting with K. EK means I am encrypting with key K. Okay, and what I am encrypting, I am encrypting both the message and the hash of the message. Okay, so in the destination, the receiver will decrypt the message first, and then the receiver will calculate the hash of the message by itself. So definitely both sender and receiver, they share which hash algorithm they are going to use. Then the destination compare with the calculated hash function and the received hash function. So if they are equal, then the destination says, okay, I'm going to receive this. Okay, so here what we are achieving, we are achieving secrecy. Why? Because we are encrypting the whole message, and we are also achieving integrity. So I am achieving secrecy and I am achieving integrity here. Because if slightly the message has been changed, then I can definitely find out what has been changed. Okay, so nothing can be changed here. এটা কি বুঝা গেছে কি বলছি আমি? কোনো question? No question. Okay, let's compare with A and B. In B, we are calculating the hash and we are encrypting only the hash part, not the whole message. Then I am adding that encrypted hash with my message M. So at the receiver side, I have to decrypt here. I have to decrypt that encrypted hash and I have to calculate the hash by myself. Then I can compare, and if they are equal, then I receive the message. So what I'm going to achieve here?
Integrity.
Only integrity. I'm not achieving secrecy here because the message is open. The message is plain text. But which one is faster?
Second one.
Second one is faster. Why? Because we are encrypting only the hash part, and the hash part is very small, maybe 64-bit or 128 bits. So this is way faster. The B is way faster than A. But remember that I'm not achieving secrecy. So it will depend what I'm sending. Okay, so what I'm going to do, whether I'm going to use A or B, it comes from my requirements. Say if I'm sending something that is already public, say for example, I am sending weather report, I am sending the update of share market, okay, something those types of value. So those values are already public and I don't need any kind of secrecy for those values, but definitely I need integrity. Okay, so then I can use option B. Now what do we have in option C? In option C, I'm sending the message, and with the message I am adding some secret value. Okay, I'm not encrypting, I'm not doing any kind of encryption. Just with message M, I am adding some secret value. Okay, and then I'm calculating the value of hash and I'm sending it. Okay, so at the receiver side, I must know this same secret value. So I have to add that secret value first with the message M, then I have to calculate the hash. Okay, and then I can compare. So remember that both of them must know which S or what is the value of S they are going to use, but they are not encrypting anything, they are not calculating any kind of encryption here. So here also I can achieve integrity. Why? Because nobody knows the value of S. Okay, and this is the key idea behind cryptographic hash function. Okay, So here they have said that this is also known as keyed hash function. That keyed or keyed part is our S here. Okay, so we don't need always, we don't need encryption all the time. We can use some secret value instead of encryption, and we can achieve the same thing. So here also we achieve integrity. So here they are showing another example where they have mixed D and A together. Okay, so here you are taking M and then with M you are adding S and then you are generating the hash and you are encrypting everything. Okay, the hash and the okay, so they are encrypting everything, and here at the receiving end they are comparing everything. But now I can think another option. Yeah, that is coming here. Okay, that's why I was looking for that option. So here I'm not sure what is the extra benefit here. I'm really not sure, because what I can see, I can gain secrecy and integrity here. So this option, I truly I cannot find any extra benefit, because here I am getting secrecy and integrity, the same thing. But this is truly, this is really what we are looking for. So here I'm taking message M, I'm generating the hash. Now I am encrypting the hash with my private key. So now we know what is private key, right? So say for example, I'm using RSA here. So I am encrypting with the private key of RSA. So I am adding the message and the encrypted part. So at the receiving side, the destination, you have to decrypt it. So since I have used my private key, definitely you need my public key to decrypt this. And who knows my public key? Anybody knows my public key. So who can verify this? Anybody can verify this, provided that he has my public key. And then he can compare hash value and the decrypted value. So what I am achieving here? Definitely I'm not achieving secrecy here, because the message is in plain text, but I am achieving integrity definitely, because I am using hash. So what else I am achieving here?
Sir, authentication.
Okay, what types of authentication? Or what do you mean by authentication?
Sir, user authentication.
Okay, so B is now sure that what? So A
That the data was sent from A.
Exactly. So now B is sure that the data was, you can say not sent, you can say originated, okay, or produced. It might be sent by somebody else, but this is sure that it was originated, or the source or the original source was A. Okay, so this is known as data origin authentication or source authentication or simple authentication. So why? Because I have decrypted. In just consider what B is concluding, how B is coming to the point. B is concluding that I have decrypted with the public key of A, and I have compared the hash and I have found the same hash. So that means the hash part is correct. That means nothing has been changed, definitely. So since I have received the correct hash by decrypting the public key of A, that means definitely it was previously encrypted by the private key of A. Otherwise, I cannot find the correct hash by decrypting the public key of A. So definitely it was encrypted by the private key of A. And who knows the private key of A? Only A knows the private key of A. Okay, so definitely it was originated by A. Okay, now you can say what happens if the private key is compromised. That's not our problem. That is the problem of A. A must keep his private key secret. If he cannot maintain the secrecy of his private key, then his identity will be compromised. That is not my problem. Okay, so here we are achieving integrity and authentication, or the data origin authentication. Now, if we want to achieve everything, that means if we want to achieve secrecy, then integrity, and then authentication, what can we do? Then we can mix B here, like B from here, and A from here. So I'm taking the message, I'm calculating the hash, I am encrypting the hash with my private key, and then I am encrypting everything with a symmetric key K. So the same symmetric key must be shared with B also. So now I am sending everything. So at the receiver side, I am decrypting with my K, the same K, and then I am calculating the hash by myself, and I am decrypting with the public key of A. Okay, now I am comparing. So now my question is, what was the problem here in A here? Why we could not conclude that this message was definitely generated by A? We are also using a key here, right? K. And that K is a
But
symmetric.
sir, this was not the private key.
Yes, this was a symmetric key. So what is wrong with symmetric key that we cannot conclude who generated this message?
Sir,
Because
symmetric key is known by all.
symmetric key is shared among more than one entities. Okay, say for example, you are three of your friends are sharing the same room, and all of you have duplicate keys. Three persons, all of them have the same duplicate key of their room, and now something wrong has been done. Maybe something has been stolen from your room. Then can you conclude who did that or who was responsible for that? You can never conclude because all of them have the same key. So you can never say who opened the room, who locked the room, nothing. Okay, anybody can do that. Anyone from three of them. So here, this message, that is this part, this message can be generated either by A or by B. So B can even generate this message and claim that, look, this message is coming from A and A has generated this message. So if you have to give a verdict, you can never say whether B is correct or wrong. Okay, unless there is other ingredients inside the message like timestamp or maybe some random values or maybe some values which belongs to A or B. But if that is not the case, you can never conclude who has generated this message. It might be generated by A, it might be generated by B. So the symmetric key, there is no one-to-one mapping between a key and the user. Okay, because the same key is being shared among more than one entities. But the public key or the private key, that is the private key, is mapped to a specific person. So we can achieve authentication here. We can achieve authentication here. So if you want to achieve everything, that is secrecy, integrity, and data origin authentication, then you must use this option. Okay, so these two slides are very important to understand the main essence of this course. Okay, this slide and the slide that we have used here, these two slides are very important. Now we have some definition for hash function. The first one is pre-image. So what is pre-image? For a hash value h, small h, we say that x is the pre-image of h. So what is x? X is just our message m, nothing else. Same thing here. They have just changed the notation. So the message itself is the pre-image of the hash value. Since h is a many-to-one mapping. Why many-to-one mapping? Can anybody tell me? Why many-to-one mapping? So where is the mapping? The mapping are here, right? We have m and we have h, right? Many to
স্যার
one.
দুইটা ই প্রাইম এম এর জন্য একটা এইচ পেতে পারি।
Exactly. This is possible. This is always possible that for more than one m, we have the same h. That's why this is a many. Many is on my left side, to one on my right side. So this is a many-to-one mapping. Since h is a many-to-one mapping, for any given hash value h, there will in general be multiple pre-images. In fact, we have discussed everything before, just we did not use the word pre-image. So for any given hash value h, there will be in general multiple pre-images, but our collision says that we have studied before here. But our here our one-way property and our collision-free property, they says that although there exist multiple pre-images, you cannot find intentionally. Remember that. So they have said that collision occurs when we have x is not equal to y, but hx is equal to hy. Okay, so this is known as collision. Okay, and collision is possible. We are saying that collision is always possible, but intentionally you cannot find out the collision. That's the point here. So we are using hash functions for data integrity. So collisions are clearly undesirable. Okay, this is possible, this is there, but this is undesirable. That's the point here. So what are the requirements for a good hash function? First of all, the variable input size. So h can be applied to a block of data of any size. Fixed output size, h produces a fixed length output. Then efficiency, hx is relatively easy to compute. Remember that always in our cryptography course or anywhere, we always consider that h is very fast. Okay, even h is always very fast with compared to symmetric encryption. If you compare symmetric encryption and h, we consider that h is even faster than symmetric encryption. So hx is, okay, again, just give me a second. Hello. Walaikum salam. Ji. Okay, so if we go back, so efficiency is hx must be very fast. So hx is relatively easy to compute for any given x, even the size of the x is large. Okay, so making both hardware and software implementations. So you can implement hash function, say for example MD5, another very popular hash function. This is always used in hardware. So most of the times hash function is also implemented in your network card. Okay, now another requirements is this must be pre-image resistant. So we have already explained what is pre-image. Pre-image means one-way property. So for any given hash value h, it is computationally infeasible to find y such that hy is equal to h. Okay, so that means if I give you the value of h, you cannot find out intentionally any y such that hy is equal to h. So I will give you the hash value. You cannot find out any message which will map to that hash value. So this is known as one-way property or pre-image resistant. Now, second pre-image resistant, that is weak collision resistant. What is that? That is for any given block X, it is computationally infeasible to find Y that is not equal to X with Hy is equal to Hx. So here I will give you the message M or the message X. Then you will find another message and both messages will map to the same H. So that is not possible. That's what they have said. Now, what is collision resistant or strong collision resistant? It is computationally infeasible to find any pair. Okay, remember that these two, this one and this one, they looks almost identical at first. But what is the difference? The difference is here I am giving you x. Okay, I am giving you x and you are finding y. And then hy is equal to hx. And the second one, it is saying that you will find the pair. So I'm not giving you anything. I'm not giving you x or y or anything else. You are finding a pair where x and y are not equal, but hx is equal to hy. So this is known as collision resistant. Okay, so hopefully I can make it clear the difference between three: pre-image resistant, second pre-image, and the collision resistant. And the final one is pseudo randomness. Okay, don't forget the word pseudo. Okay, pseudo means this is not actually random, but it appears random. Okay, so output of H meets standard test for pseudo randomness. What does it mean? It means here we have said, say if I give you a distribution from 0 to 63. So if this is a pseudo random, then you will find that this is evenly distributed. Okay, so if I give you an M, you calculate the age, maybe it is 7. Then I'm giving you another M, you are calculating, maybe this is 31. So if you calculate, say for example, 60 times, maybe there is no repetition for different values. Then I can say, okay, this is a pseudo random hash function. But if you find that there is a biasness, say for example, most of the times the values are from within 0 to 20, or most of the times the values are from 40 to 60, or if you find that just after calculating 5 hash function, you can find collision just after 5 or 6, and then definitely this is not a pseudo random. Okay, to understand the pseudo random, just think that definitely I'm expecting that all of you did some kind of programming And in programming, there is a random function, right? In all kind of programming language, in C or Java or whatever. So there is a random function. And in some cases, you have to start with some seed or something like that, okay? So then you can say the range of the random function. And if you remember, you can easily remember that if you call the random function maybe 10 times or 15 times, there is no repeat, okay? So that random function was a pseudo random function, okay? So how to generate random number? Remember that this is a research problem, and how you can generate a random number. There are different ways. You can generate it from your clock, you can generate it from your time, or maybe some keystroke, or maybe the browsing pattern of the user. Like there are different ways, okay? Or maybe from images. So this is a research problem. This is not an easy problem. This is a very difficult problem to generate random number. Even people say that you can never generate a random number. What you can generate, that is a pseudo random number, okay? So those are part of mathematics. So we are not going to that detail, but we are saying that output of age will be pseudo random. So there are some standard tests, and that will pass that standard test. So these are the requirements if you want to design a new hash function. Okay, so say you want to design a hash function, then you must meet these requirements. That was the point here. Okay, so what was SHA? SHA means secure hash algorithm. So SHA was originally designed by NIST and NSA. These are two US-based research institute and government specification institute. So they designed SHA in 1993, and this was revised in 1995, and then it was known as SHA-1. So US standard for use with DSA. DSA is one of the signature scheme like RSA or Diffie-Hellman. DSA is one of them. And US says that they want their standard is DSA. So in DSA, they use SHA algorithm. Not only in DSA, in many standard digital signature scheme, you will find that they use SHA. And this is based on design of MD4 with key differences, and it produces 160-bit hash values. So the fixed output that we have just said, this is 160-bit. Recently in 2005, results on security of SHA-1 have raised concern, okay? So it was compromised, and people found that they can break. Break means they can find, or they can break these three properties. Okay, so if you can break one of these requirements, then you can say I can break SHA algorithm. Okay, so to break SHA algorithm, you have to break one of these three properties. So now it was revised and known as Secure Hash Standard. NIST issues a revision FIPS in 2002. And like, so now there are different SHA, SHA 256, SHA 384, SHA 512. So what is that 256 or 324? Those are the length of the hash. So previously it was 160-bit. Now these are the length of the output. Okay. So there are different standards, 3 additional versions. So it was designed for compatibility with increased security provided by AES cipher. Okay. So there are different versions, and you can find that this is like this 256 or 384. This is just related to your message digest size. So that means the output length. So if you use SHA 512, your output length, that is the length of your hash, will be 512 bits. And what is message size? Message size means the maximum message, the maximum allowable message, the maximum length of the message it can handle. Okay, but I'm not sure, we have to look into this, whether this size is in bit or byte. Okay, remember that in networking, when we say maximum allowable messages, you must mention the unit you are working with. Okay, sometimes we use bit, sometimes we use byte. Normally we don't use kilobyte or megabyte here. Okay, most of the times either we use byte or byte. Sometimes we use octet. Okay, octet means 4 byte. Octet, I think, if I am not wrong. Octet means 4 byte. Okay, sometimes we use octet too, but mostly we use bit. Sometimes we also use byte. So when I say message size, I guess this is bit, but I have to look into it. Definitely we have it later. Now, what is the block size? Block size means you divide the whole message into different blocks. And this is in bit, that is, I'm sure. Block size in bit. So we have also word size. Right now, I cannot remember what is word size. Maybe later we have it. And number of steps. So SHA-512, there are 80 repetitive steps. So you do the same thing 80 times. And here previously, we also do the same thing 64 times. Okay. Okay, now here we have the length, and here we can see that the length is in bits. But this is very long, 2 to the power 128 bits. Okay. So remember that this is a very long message. So the algorithm takes as input a message with a maximum length of less than 200 128. So I will explain later why this is 128, from where it is coming from. Remember that in networking, everything is defined by the header. Okay, whatever I say I say IP version 4, IP version 6. So what IP version 4 can do or what it cannot do, everything depends on the header of the IP version 4. So when I design any kind of protocol, I must first set up the requirements of that protocol, what I am expecting from that protocol. Then, based on those requirements, I define the header. Okay, so if I say something that I need this from this protocol, then definitely I have to keep something inside the header to meet that requirements. Say if you say, I want error checking here, then definitely there must be some mechanism of error checking, and that mechanism will be implemented through the header. Okay, so whatever services you want, you have to implement that service through the header, because header is the only part that is being processed by the sender at the same time that is being processed by the receiver. So whatever you write inside the header as a sender, remember that you write that for the receiver. Okay, and here comes that layering part, that we say that in a layered protocol, we have a specific function for a specific layer, and the layers are peer, right? We use that. One layer is peer to the same layer of the other side. That means sender and receiver. So that layering part, the layering protocol, the layering architecture, whatever you say, everything is accomplished by the header of a specific layer. So when I say that the maximum length is 102 to the power 120 bits, that means there is some relationship with the header. There must be some space to write this length, and that space allows this bit. That's why we are using this. Okay, I'm going to explain it later. So here we produce a output, and the output is 512-bit message digest. So the input is processed in 124-bit blocks. So if you have a large message which is larger than 1024-bit, definitely most of the messages will be more than 1024-bit, because 1024-bit is small, it's not a very big size. So what you do, you divide the message into several blocks. Okay, and then you calculate the message by block, and at the end of the last block of processing, you generate the message digest, the final message digest. Okay, so the processing consists of 5 steps. So okay, maybe we can discuss this next class, because I cannot complete it now, and if I start, I will stuck in some middle step. So let me give you attendance first. Okay, so any other question? I'm not sure why you don't have any question. Either I cannot explain anything so that you don't understand anything, or I explain so clearly that you don't have any question. আমি জানি না যে আমি এখানে কোনটা ধরবো আর কি। Okay, so give me your attendance. Raihan,
Present, sir.
Tauhid,
Present, sir.
Mahfuzul Islam, Azhar,
Present, sir.
Ryan Ali,
Yes, sir.
Talha,
Yes, sir.
Abdullah,
Yes, sir.
Adnan Rashidul Islam,
Yes, sir.
Abid Hassan,
Present, sir.
Mazharul Haq, Sumaita,
Yes, sir.
Mustari,
Yes, sir.
Rafid,
Present, sir.
Afrin, Mominul Islam,
Yes, sir.
Said Abdullahi,
Yes, sir. Present.
Raunok Abdullah,
Yes, sir.
Muna, Jannatul Naim,
Present, sir.
Salikin
Present,
Firdaus.
sir.
Okay,
Present, sir.
Sajjadur Rahman, Sajid Ahmed,
Present, sir.
Imtiaz,
স্যার ইমতিয়াজ ছিল স্যার, ওর নেটের লাইনে সমস্যা হয়েছে, একটু আগে আমাকে ফোন দিয়ে বলছে আপনাকে একটু বলার জন্য।
আচ্ছা, রুবাইয়াত, সাইদা তাবাসসুম,
Present, sir.
দিদারুল
Present, sir. Sir, Rubayat, present, sir.
Okay.
Yes, sir.
Didarul Abidin, yes. Okay.
Yes.
Muhammad Jama,
Yes, sir.
Fahad Hassan, Zibril Adan,
Present, sir.
Abdullahi Hassan,
Yes, sir.
Nuzat, Onik Choudhury,
Yes, sir.
Ikramur Rahman, Abdullah Hil Farooq. ওকে, আর কাউকে কি মিস করছি?
স্যার আফরিন মাকসুদ স্যার প্রেজেন্ট।
হ্যাঁ,
আমি স্কিপ করছি হয়তো।
আচ্ছা, আপনি প্রায় কেন জানি স্কিপ করেন। ফাইন, ওকে, দিছি। আর এনিবডি এলস? Okay, so next class তাহলে ইনশাল্লাহ we are going to take our next test. So the syllabus will be RSA. Okay. আচ্ছা ফাইন, তাহলে আমি কনক্লুড করতেছি। ইয়েস
স্যার, চ্যাপ্টার 5 কি পুরোটা ক্লাস টেস্ট নাকি শুধু ফার্স্ট ফাইনালের পরে ফার্স্ট যে ক্লাস দিচ্ছে সেটা?
the whole chapter 5, the whole slide, whatever we have studied in that slide.
Thank you, sir.
Okay, so if you have any question or if you want to discuss, maybe on Thursday or on Friday, send me an email or give me a call. Okay, just give me some time so that I can announce and the others can join too. Okay, if required, but please don't request me to repeat the whole lecture. মানে এটা আমার জন্য খুবই ডিফিকাল্ট হয়ে যাবে যদি আমাকে বলেন যে আবার পুরোটা ওইখানে যে বোঝানো। If you have any specific question, definitely I am there. I will try my best to help you. Okay, so again that means I'm expecting that you will try, then you will come to my